Eu vou passar, eu só vou aí. Boa tarde, pessoal. Actually, to introduce our speaker, I'm going to invite the Professor Carlos Fiore to make to comment about his biography.
Hello, everybody. No, it's a great pleasure for me, for the Institute, to have my colleague and collaborator, Bart Cleuren from Hasselt University. Only some details about his career. And he concluded his Bachelor in 1997 in Hasselt University. In 1999, he concluded his Master under the supervision by Professor Christian van den Broek. Christian van den Broek was a reference in this area of non-equilibrium statistical mechanics and in stochastic thermodynamics. In 2004, he concluded his PhD, also under the supervision by Christian van den Broek. He did a couple postdoc on a part in Hasselt University, another part in Germany, under the supervision in collaboration with Peter Feynman. Raymond. Okay. Since 2008, he is professor in Hasselt University. Now he's associate professor. We have developed a collaboration, bilateral collaboration, and he was the supervisor of my PhD student. And it's a great pleasure to have here in our institute. And he will talking about the Feynman ratchet-and-pawl revisit. Thank you, Bart.
Okay, thank you. Can everybody hear me like this? Yes, okay, great. So thank you for having me here. It has been so far a very pleasant stay here in Brazil. It's my first time. I enjoyed and I hope to come back more often. So I will talk today about the Feynman ratchet-and-pawl, and not just what we have done, but I will also give a little bit of context regarding this. And this research is done, as you can see, it's in collaboration with Dr. Ralph Eichhorn from Nordita. It's the Nordic Institute of Theoretical Physics in Stockholm, Sweden. Maybe, as I am from Belgium, Hasselt University, I will just show you where it is. Well, you might have heard of Belgium, or you might have heard of, sure, I think. And Hasselt University is located in the east of Belgium. We are celebrating our 50th anniversary, so we are a pretty young university. And I am part of the research group called Theory Lab. It's the theoretical physics research group. Our focus is mainly on statistical physics, and it used to include in the past there was stochastic processes, neural networks, stuff like that. It's a small group. We have now 2 professors and 7 PhD students. And as Carlos already mentioned, the reason why I'm here is because one of the students of Carlos, he had a PhD defense this week, and I'm co-supervising. So it's a very good opportunity. We had a common project. It's a joint PhD. And you know, I can make a little bit of advertisement. If you are seeking collaboration in Belgium, please check out also. You can ask me later on. Okay. So I will start now with the main topic, and it's on the Feynman ratchet-and-pawl. And I think the Feynman lectures on physics are very well familiar to most of the people here in the audience. It's a device, as you can see here. Feynman introduced it in a chapter 46, after he introduced the basics of thermodynamics. And in the chapter before, he explained about Carnot efficiency and that you cannot convert all the heat from a hot reservoir into work. And well, he wanted to give an intuitive explanation on how that would be possible, right? And so he came up with this device. It's the ratchet-and-pawl machine. And what is obvious to us, of course, it's you know, you see the ratchet here and the pawl there. So this gives the impression that this machine, it rotates in a certain direction, right? And I mean, he came up with that in '63, but it has already a very long history. And I just mention a few examples here. The history and context, number one, that's the eternal quest for the search for perpetual motion, right? And this machine, it gives the impression that it will continue to rotate in one direction. Even, I mean, now I put here the temperatures equal, right? I mean, it goes back already from Maxwell with the Maxwell demon, right? That, I mean, it was a, how to say, imaginary creature that could make it possible to convert heat from a single heat source, right? And I mean, later on, Léon Brillouin, he came up with an electrical circuit just with a diode and a resistor. And this would, it also gives the impression that the fluctuations that are present in such a circuit could induce a current. But we all know, of course, that when you're in thermal equilibrium, this is not possible, right? But it's far from obvious when you do the analysis. That's already important. Now, second history that I want to give is it's about the heat engines and Carnot. Well, here on the slide is just a stirring engine as a typical example of a heat. So the basic idea is that you have a hot reservoir and a cold reservoir. We know that when there is a temperature difference, there will be a flow of heat from hot to cold. And the idea is that you can use an engine to convert part of this heat flow into work, right? And I mean, when the steam engines appeared, of course, there was the big question of what could be the possible efficiency of such a machine, right? And it was Sadi Carnot in 1827. He came up with the Carnot efficiency, right? As you can see here. So every heat engine, the efficiency of every heat engine is limited by this maximum value. So it's 1 minus the ratio here of the temperatures. Okay, but the context. So we have the perpetual mobile motion, and we have the heat engines and Carnot. And now I will not go very much into details on the Feynman analysis. You can find it in his textbooks. But Feynman, he did an analysis, and you know, he essentially what it boiled down to, he described this machine, and he thought it was possible to have it operate with Carnot efficiency. So, I mean, first thing, it was obvious for Feynman, and it's also now obvious to us, that when the temperatures are equal, it would not rotate. There's no preferential rotation in the system, okay? But what he then did, he considered also the case with the different temperatures. And then he discusses, and he came to the conclusion that this machine, it would be possible to operate it reversibly, so no entropy production. And then the efficiency would be the Carnot efficiency, right? So that was the main conclusion in the lectures. Then, so this is 63, when Feynman wrote this down. And then, well, it took some time. It was in 96 by Juan Parondo and Pep Español. They had an article in American Journal of Physics where they criticized the analysis done by Feynman. And I mean, their main argument is that you see the machine here, it has only a single degree of freedom, which is the rotation, which means that it is always in contact with the two heat reservoirs, always at the same time. So this is very unlike the Carnot, the ideal Carnot cycle, right? And because of this simultaneous contact with the two heat reservoirs, I mean, they argue that it's impossible that this machine would work. Possible. And they do some analysis. It's a phenomenological description based on a Langevin. So in this case, I mean, there's only one degree of freedom, and they take the coordinate x, and they write down here what you see, the Langevin equation. It has the usual friction terms coming from the paddles and the surrounding gas. Yes, and then you have also the two noise terms, and so the noise is a reflection of the collision that the machine has with the surrounding gas particles. And so they calculate, for example, the heat conduction. And of course, I mean, we all expect that, when you are in simultaneous contact with two heat reservoirs, there is a flow of heat coming. And they calculated it's proportional here, the difference in temperature. And because of that, because of this heat flow, which is always there, you cannot avoid it, the efficiency must be lower than Carnot. Okay, and it's all very nice. So we have had the Feynman analysis. We have had now this criticism. So far, for me, it was not really, I was not very happy or content with it. Because, well, you see, the description here is based on a Langevin equation. And for example, some kind of friction coefficients, they're the same in both cases, on both reservoirs. It's phenomenological. And what I try to do is I try to come with a more microscopic model of ratchet, right? So that was the goal, and that will be the main part of the talk. So I want to have a discussion of the Feynman ratchet-and-pawl based on first principles. And we make it as simple as possible, so that we hope we can get some exact results. It's completely classical mechanics, so it's very intuitive. We can do a lot of calculations with that. And as I say, I also want to use a minimal set of assumptions. Right? And if you think of the original engine, the ratchet-and-pawl, what is essential there? It must have a rotational asymmetry. That's one ingredient that I need. And the second ingredient is, of course, the non-equilibrium. Okay. So what we came up with is the device that you see here. So, well, if we go back here to the original one, have, of course, the ratchet-and-pawl, which how to say, it describes the asymmetry, the rotational asymmetry, right? But such a pawl, there's a spring there. The teeth here, it's difficult to describe, and I don't like that. So what we did is actually, we have in yellow here a device which is also rotationally asymmetric, and we hope, it will also do the job. And well, Feynman draw a bug here as a weight, but they just use a ball, as it doesn't really matter much. And so for the rest, it's pretty much the same as the original ratchet-and-pawl system. Okay. Now, so as I said, it's in yellow. That's our device. We just model it as a rigid body, so there's no deformation, whatever. It's also a single degree of freedom, right? It's just a rotation around the rotational axis. It has a mass, has a motion of inertia, and it's a rotational asymmetric, right? Well, you might think, if you look at this specific example, that it's not. I mean, rotating left and right is not, there's no difference. In fact, in this case, the difference comes also from the fact that one of the objects is in a hot reservoir and the other is in a cold one. So that adds to the spatial symmetry. And the non-equilibrium ingredient, that's just each object here is surrounded by an ideal gas, classical ideal gas, at a given temperature and a given density. Basically, our model. And what we want to do now is we want to study how this object behaves. How does it rotate? Is it able to convert heat into work? And so on and so on. And if you think of it, there's not much that can happen. I mean, what can happen is that there are collisions with the gas part. That's the only thing, basically, right? So it's an exercise, classical mechanics, to know what the effect is of a single collision, right? And well, it's not really straightforward, you know. It's a system with a constraint, so you can take into account these forces of constraint. But in fact, you know, if suppose that our object is rotating at angular omega, and then you have a collision, I don't know, you have a collision at this point, x and y, with a gas particle with velocity v, right? Then this equation tells you what is the change in angular velocity, right? It's a purely elastic collision, instantaneously, and that's it. Okay, so that's, yeah, one of the things. This random collision makes the object, it makes it rotate. Okay, then the second thing, of course, makes the object rotate. The external torque. And the torque, you know, it's a basic equation that changes the angular velocity. Okay, maybe I will also notify here that, you know, in this collision rule, you know, there's it depends also on the ratio of the masses, obviously. And there's this factor here, the G alpha, which it includes the geometry of the object, more or less, you know, because it's the angle at which the collision occurs. It's important, of course. Okay. Now, we discussed what happens with a single collision, but of course, it's surrounded by a ideal gas, so there are many collisions. And we don't know when a collision occurs. The only thing what we can say is, what we can ask is like a transition rate. The probability per unit time to have a change in angular velocity from omega to omega accent. Okay. And to calculate it, it's fairly straightforward to write it down. You see, it's a integral over the whole surface. Okay. What else do we have? Yeah, we have the velocity distribution of the ideal gas, which is at a certain temperature, right? And then we have here this is the Maxwell velocity distribution, right? Because we need the statistics of the incoming particles. And then there is here, yeah, you have the delta, which picks out the incoming particles, which gives just that change in angular velocity that you want. And then there's also, yeah, you have here the Heaviside function and some other requirements here that we don't want. We want collisions to occur from outside, not on the inside. And that's why there's some extra factor here. Okay. Now, what you also see, there's an index here, which I mean, there's a transition rate associated with hot reservoir, and there's one the cold reservoir. Okay, and as I said, there's an integral over the shape of the object. And something I have not, I mentioned it already. No, to calculate this transition rate, I need to take into account the statistics of the incoming velocities. And I take this as a Maxwellian velocity distribution, which means that my gas is in equilibrium, right? But when you think of that, you know, once a particle collided with an object, that gas particle is no longer in equilibrium. It changed its velocity, and there's no, I cannot guarantee it's certain that it is not, the distribution is no longer Maxwellian, right? So this could be problematic here. And I mean, in order for this expression to be valid, there's one thing we don't want, and that's recollisions. Because recollisions, I don't know the distribution of the velocity anymore. That's problematic. And I mean, there are here two sources for recollisions. And one is maybe if you use a non-convex objects, right? You can see there that it bounces off, and you know, it has multiple collision here. There is another source of recollisions, and that's I call it the overtaking maneuver. That is once a particle collides with the object rotates and hits the particle again. Right. You see, that's also what we don't want. And now, so to get rid of the recollisions, what do we do? Well, first thing is we use convex objects. What you see, this is all good. And to avoid the overtaking maneuver, we take the limit that the mass of the object is much larger than the incoming particles. Okay, and that's a introduce this epsilon as the square root of this ratio, and this is must be much smaller than 1. And this epsilon will also be an expansion parameter that I will use later on. Okay. Now, under these conditions, I can write down the Boltzmann-Master equation, which is an exact description of dynamics. Okay. And but even, I mean, we have a very simple system. Everything is exact so far. But to solve this master equation is still it's difficult. I could say impossible. It's not obvious at all. So, I mean, to go from here, I want to know what is the average rotation of the object, right? So what I do is, I mean, I just go from the master equation. You can go down to a set of equations for the motion, for the moments, right? So what you do is this is a partial differential equation, and you transfer it into an infinite set of ordinary equations, ordinary differential equations. But objects that appearing here, it's a jump moment. This is like an averages over transition rate. And now, I mean, basically not much has happened. Both descriptions are exact, but it doesn't really matter it doesn't help us solving it. So there's another step that we need to do. Turns out, when you can expand these expressions with the epsilon that I showed, the ratio of the masses. And then it turns out that these equations, they decouple. And this allows to get exact expressions. And you see here, I just, in orange, it's the first two moments, the average angular velocity, and also the second moment. Okay, and so these are valid in the limit of small epsilon. So I mean, the results, if you want to interpret them, there are the terms that are appearing, at least in the lowest order, they are rather simple to interpret. For example, this first term here, you know, that's the torque, external torque, and it is divided by the friction coefficient. You know, you have gamma. There's a friction coefficient associated with the cold reservoir, and there's one with the hot reservoir. And here's an expression for the friction coefficient, and I mean, the friction coefficient, as we would expect, it depends on the shape of the object. Very obvious, okay. And then, I mean, the second term is already harder to interpret. It's torque to the power 2. The third term, what you see here is actually associated with a temperature gradient. Okay, if there is a difference in temperature, then this term appears. And you see also that it is proportional to this ratio here. It's a very small term, actually. I mean, this one is way more dominant. Okay, and so that's for the average velocity. If you go to the second moment, well, maybe we focus first on this term here. Actually, this is if there would be no external torque, then these are just this description for the thermal fluctuations. Fluctuation dissipation here. It's this term here is like an average of the temperatures, but it's not just a average, but it has to do with the friction coefficient. Okay. Now this first term here, it's actually it's just this one squared. It comes from the deterministic motion. Okay. I give here it's a result from it's a comparison between the theory and the simulations that we have done. You see, well, so in blue is the theory. It's actually you see the black dots are the simulation results. This is for the ratio. I mean, small mass is 1 and the large mass is 20. So epsilon is not that small, but it still works okay. Right, and there's a difference in temperature. Right, it's theory, so we just use 2 and 1. And you see that, I mean, this is the angular velocity versus the torque. And of course, when the torque is 0, there is still an angular velocity which comes from the flow of heat. Okay. What we can show, I mean, if it's obvious, if there's no torque and the temperatures are equal, then no average angular velocity, which is, of course, what you would expect, right? Now, maybe I would, if we look again at this term, even without the external torque, I mean, the first two terms would be gone. But if you look here at this third term and imagine that the temperatures are different, it's also not obvious that there will be a non-zero angular velocity. If you look at this term, there's a minus sign here. And this minus sign, it takes into account the rotational asymmetry of, right? If it would just be circles, then nothing would happen either. So that's included here in this. Okay. I'll move forward. We discussed the dynamics. The next on the agenda is the energetics and the thermodynamics. So I already discussed, we have random collisions. We have a deterministic torque. And it's rather straightforward to associate the thermodynamic quantities with that. I mean, work is classical mechanics. And heat, well, I mean, if you think what you see here is the angular velocity change of the object due to a collision. But of course, there are corresponding changes in velocity for the gas particles. And you can just calculate the kinetic energy of the gas particles before and after a collision. And this change we call, I mean, we associate it with the heat. And I mean, from this, it's again straightforward. We can incorporate these quantities into our framework in the Boltzmann-Master equation. It becomes a little bit more elaborate because, well, we want heat and heat. I mean, there can be heat exchange with the hot reservoir and there can be a heat exchange with the cold reservoir. So we have to take into account. Okay, and then, well, it's again difficult to solve this straight in a direct way. So we look at the moments. And actually, we are interested mainly in the first moment, which is the simplest thing to do. So, I mean, for the work, the time derivative of the work is just the torque times the average angular velocity. And for the heat, well, the heat can be expressed again in terms of the jump moments. Okay, it's straightforward. There's a conservation of energy. I mean, if work and heat, the change here has to be equal to the change in the kinetic energy of the rotation. Okay, so if in a stationary regime, then this, of course, you have just a conservation of energy. Entropy production, I also need that. It's just related to the exchange with the heat baths, because our object itself it's a rigid body. It's just there's a single degree of freedom. So all the entropy differences, it appears in the exchange of the heat baths. Okay. Now, we also want to have analytical expressions for these first few moments. And now, instead of just the epsilon expansion that I used in the dynamics, there is another expansion that we need to take. Because you can imagine that, I mean, there's differences in temperatures. There's the external torque. It's highly nonlinear thermodynamics when you think of the temperature differences, right? So at some point, I want also to do an expansion in thermodynamic forces. And I need to identify that. I start from the entropy production, use conservation of energy, and then I can write the entropy production as this bilinear equation here. J1, J2, and then you have X1 and X2. These are the thermodynamic forces. One is associated with the torque, external torque, and one is associated here with the difference in temperature. And the corresponding fluxes for J1 is just the angular velocity, and for J2, we took here this difference in heat. between the two paths divided by 2. And then you do the expansion, the epsilon expansion. You also do the expansion in the thermodynamic forces. It's a lot of work, but it's basically algebra. And then you end up with very long expressions. I will not go much into detail. What I want to say is that, well, I need to check something. When there's no torque and the temperatures are different, then it's straightforward that there's a heat flow from one object, from one reservoir to the other. And this is exactly what the criticism by Parondo and Español, they were saying, because it's a single degree of freedom in contact with two reservoirs at a different temperature, so there is a heat flow. And I mean, this was already a first check that our calculations were correct, is that they all have the opposite sign. So heat is flowing away from the hot reservoir and entering the cold reservoir. So it behaves as we would expect. All right. Now, what I show here is also, again, a comparison with the theory and the simulations. If you look at the scale of the vertical axis, you know, for average work, this is 10 to the minus 6, compared to average heat, that's like 10 to the minus 4. So there's a big difference, which means actually that our machine is very, very inefficient. I mean, the work output is 100 times smaller than the heat flow between the reservoir. Okay, so it's not really useful as a heat engine. Okay, so this is what I wanted to say on the Feynman ratchet-and-pawl. There's a second example which I also would like to mention now. I still have some time. I will use the same framework that I use for the Feynman ratchet, and I will discuss an experiment done by Joule. He had this famous paper, the mechanical equivalent of heat, right, where he showed that heat is just another form of energy, right? And I mean, this is the picture you see here is a device, or it's the original device. And so the idea what he came up with, you know, you have a fluid, there's pedals in between, it's isolated. You have a thermometer, and what you do, you just have weights that dropped in the gravitational field, so you can calculate the change in mechanical energy, and you measure the temperature. And when you drop the weights, the temperature of this fluid will increase, right? So that's proof of this equivalence between the two forms of energy. And actually, what I want to do now is develop a microscopic Joule experiment. It's very similar to the framework that I have used before. So instead of a fluid, we just use an ideal gas, okay, at a certain temperature T. Instead of rotation, I take translational motion. Instead of a pedal, I use a convex object. And instead of gravity, I just have this object moving with a constant velocity in an ideal gas, okay? And the effect of a single collision, I mean, you can imagine if this object is moving with a constant velocity, it will hit some of the gas particles, and the kinetic energy of the gas will change, okay? And so the effect of a single collision is written, this theta has to do with the angle of my triangle. I just take a simple triangle here. And I move this object for a certain time. Okay, and I count all the collisions that are appearing. But you can already imagine that, I mean, I call it a microscopic Joule experiment. So you can imagine that when I put object in an ideal gas, there will be random collisions. So when I repeat the experiment, it's very likely that the amount of work that I do, it will be different each experiment, because the collisions will be different. Okay, so I mean, what I get from such an experiment is not just the average value of work, but I get the whole distribution of work values. And the nice thing, actually, we can calculate this distribution for this model. So, and I mean, it's again no recollisions. It's an exact Boltzmann master equation. In fact, we don't solve this again directly. What we do is we look at the cumulant generating function for that distribution, and this is rather straightforward to calculate. Yeah, and I will show you some results here. So this is, I move here the object with the pointy, with the tip forward. I repeat it many times. We did a simulation, and then you end up with these kind of distributions here. You see, there's also a delta peak here, which means that there's a non-zero probability that no collision occurs. That's where this delta comes from. Okay, and we do this for, you can see, I mean, there are different curves. It's for different velocities of the object. We can move it slowly, you can move it fast. And of course, the distribution will change. And another thing, there's this tau here. It's no longer the torque, it's the time that we pull the object. We can pull it for a long time, or we can pull it for a short time. And this all has an influence on this distribution. Okay. And if this object would be very large and we would pull for a long time, then actually these distributions, they would just become a delta peak around the average work value. I mean, you end up in macroscopic thermodynamics and you just have one value for the work. Now, the funny thing is that, or the remarkable thing, I shouldn't say funny, the remarkable thing is that for when you do it microscopically and you reverse the velocity, you do the experiment in the reverse order, then, I mean, yeah, the statistics of the work, it changes. So you end up with two different work distributions. And then, I mean, you could say, okay, that's obvious. No, it's the shape of the object is different, so you have a different work distribution. Now, the remarkable thing is when you take the ratio of these two distributions, you get a straight line. So what we show here, this is, let's say, the forward distribution, and this is the backward distribution. And if you take the ratio of this, it's you take a log plot, then you get a straight line here. And this is an illustration of the Crookes relation, the fluctuation theorem, which comes out here. And yeah, I mean, the way, because we didn't calculate the distribution itself, but we used the cumulant generating function. Now, if this relation holds for the probability distribution, then it's fairly straightforward to show that this cumulant generating function also has a symmetry property, and it's straightforward to validate it here. Okay, I will not I mean, it's as I said, it has to do with the relation. It's already from 1999 that it was first described. I will not go further into details, but it's I mean, it shows that this convex object moving in an ideal gas is very fruitful or a very rewarding system to study, and we have discussed the Feynman ratchet, we have discussed the Joule experiment, and there are other examples that we still can discuss. Okay, so this is basically the story that I wanted to say. So I thank you for your attention.
So the session is open for questions.
Hi, very nice talk, very interesting. So I'm still trying to understand how you have an average velocity with zero torque. Is that because the axis of the axle is not symmetric? It's not at the center of the objects. Is that it? I mean, if you go back to your when you show the collisions, it seemed that in the XY plane that you had, the center is not the geometric center of the.
No, it has not so much to do with this. I mean, if I will just go back for here. Okay, if there's no torque, then of course these first two terms are gone, and we only have this torque here remaining. This term remaining, and well, this term is always only there. That's one thing when the temperature difference is there. And then the second thing, what you see here, it has to do with the shape of the object, the geometry. And indeed, I will go to this slide. Of course, if this point is our rotational axis, if you change it, then you change the coefficients, you change the geometry.
So if that was at the center, then I mean, the probability of a collision for producing a rotation this way or the collision on the other side would produce the other way would cancel out.
It could cancel out. Yes. Yeah.
Other question?
Hi, Bart. Just a question. Is that possible to find some optimal shape of the object that maximize the work?
Yes. It actually it kind of resembles this thing what I show here, which is highly non-trivial. But yeah. But yeah, we have. But for other, we did it. But the thing it doesn't really change it so much. I mean, the performance stays. It's not so. It will never be a good engine, but you can optimize it. Yes.
Sorry, along the same lines, is there a more symmetric shape that still gives you a rotation, but funny as this one, or do you actually need to be offset in a few directions so that you can get those terms to be non-zero?
No, I show, where is it? I mean, it would work for this perfect. Yeah. There's no problem there. These objects are easier to calculate, of course. They just have the shape function. It's like a sum of Dirac deltas with the angles. So it's straightforward to calculate. Yes.
We'll have one more question.
Hi. One of the arguments about that Feynman used was based on the asymmetry of the two objects. you have a
Yes.
pole and then you have something different in the other side. And your machine here has the same object, it's just rotated. And so the asymmetry, it's just on this, the form. Yes, they are exactly the same, just rotated. And I wonder if you have some comparison of this with that of Feynman, because it's important to use his arguments on these two different objects and to compare with your machine. I'm not I'm a little bit confused. And also when you have that difference of 100, the two order of magnitudes, you use, or you are based on a series expansion in an epsilon. What if epsilon, it's not just it's not so small? And have you studied the other terms, or
Yes,
it's
yes,
not
yes.
not very well explained, and I'm a little bit confused about.
Okay, okay. Well, first try to answer the first question. So it's, if I understood, it has to do with the shapes, right, of the object.
Shapes, the two different shapes of
Yeah.
the machine of used by Feynman and your
Yes,
your
yes.
machine.
Well, I mean, if you look at the Feynman shapes, you immediately see, well, this pedal system is not convex, which we didn't want,
Yeah.
and this is way too complicated.
Uh-huh.
So we made an abstraction of it. I mean, the basic ingredient we need is a spatial or rotational asymmetry. That's the basic ingredient. And for, well, this object has this spatial asymmetry, but you have, I mean,
But they are the same.
yeah,
They rotate.
but the thing is,
Yeah.
this one is in the hot temperature, hot reservoir, and this one is in the cold
The
reservoir.
same as Feynman's.
Yes.
Yeah.
But that, I mean, this also adds to the spatial asymmetry. There is a difference between rotating left and rotating to the right.
In your machine, you mean?
Yes, yes, because I mean, if
Yeah.
it
I've
goes this way,
seen this.
this is, it's moving in the hot reservoir. The density could be much higher here than it would be here, right? So there is a spatial, there is a rotational asymmetry. It might not be the best example. You can have different shapes, whatever you want. This is, I mean, it's for illustrational purpose. It's the enantiomorph setup, but you can, if we would flip this and make it like that, there would be no spatial asymmetry and it wouldn't work. Does this answer your first question?
Yeah, I must think about this. Okay, all right.
And-
And the other one, it's about the series
Yes.
on
Yes,
the
yes,
rate of
yes.
the two M's. Yeah, the two mass.
Yeah, so it's not so easy to explain, but we do think it has to do with our epsilon expansion because our object is very heavy.
Yes.
And
yeah.
just for it, I mean, the average angular velocity is very slow. But on the other hand, it's in contact with gases, so it's fluctuating a lot. Whereas the average velocity is very slow, which means that the heat conduction from one side to the other is very large compared to the work that is being done. That's the reason. And it's an artifact from the fact that we need to use this epsilon expansion in order to get analytical results. If you would do a simulation, it will be different.
Okay.
Yes.
Just a second. Sorry. This is podcasting.
I was wondering what would happen if there was no gas, no cold gas, if it was empty box on the right side.
Here it would be empty. What would happen is well, you know, this weight, the weight would drop, and you would, at some point, it's rotating fast enough so that friction will counteract the force or the torque.
Okay, but if you so you've set the zero torque, for instance.
Zero torque.
Yeah.
Okay, so zero torque and this empty, then the object is in contact with one heat reservoir, and it would just fluctuate. It would not rotate, right? If you look at the,
I'm not sure, but okay.
no, it will not rotate, even if it's asymmetric.
Because you have friction. So friction is a
No,
fact of time reversal symmetry. And you should have friction. You don't have viscosity.
No, but there is friction, but I mean there are elastic collisions.
Elastic collision. Okay.
See, and that, if you are right, if you would take an inelastic collision, then such a asymmetric object would also start to rotate. Yes. Yeah, exactly.
Thank you.
You're welcome.
Do you think that this is the molecular motion, molecular?
It is, yeah.
Okay.
It is. You can think of it as a molecular motor, or yeah.
So the molecular motor is not a chemical type of motor, but a mechanical.
Oh,
That's
yeah,
my question.
or maybe better term would be Brownian motor. Yeah, would be maybe the more appropriate.
Take one more.
Hi, Bart. Building up on Carlos' question, didn't you calculate the efficiency with the simulations? Isn't it possible to do that?
Yeah, yes.
Okay.
But yeah, I cannot remember. I don't remember, but yeah, we did.
Because I've seen comparisons. You showed us comparisons between various quantities.
Yes, but
calculated from the simulations and from the expansion.
Yes,
and
but
it seemed that they would all agree to a very high precision or reasonable precision.
Let me here. So this is actually for the ratio 1:20, which is, I mean, it's not epsilon, and it still works. Rather reasonably.
So that's why I'm asking whether you calculated the efficiency with within the same simulation. And
I have to check it.
Okay.
But yeah, and when we do the calculations, we also keep track of recollisions. We count them because, I mean, they only vanish in epsilon to 0. For any finite ratio you have, but even for this ratio is very, very small. The amount of recollisions, yes.
Okay.
Yes.
Thank you.
Okay, further questions? If not, let us thank our speaker again.